When you look to the night sky, almost every single dot and soft glow that you can see with your eyes has been catalogued, named, and precisely mapped. The night has been so thoroughly documented that a single photo of it can tell you exactly where you were looking and what you were looking at. Our galaxy alone has tens of thousands of nebula, hundreds of billions of stars, and countless other mysterious deep space objects. So the question naturally presents itself: how can you, in your backyard, use a small telescope or even just a camera to find objects thousands or even millions of light years away? Having a strong understanding of the night and the different coordinate systems used is foundational in astrophotography. Hello, and welcome to the first video in an incomplete guide to astrophotography. In this video, we will cover one of the most important aspects of astrophotography: navigating the night sky. We will cover the theory behind different coordinate systems, so that in the future we can apply this knowledge to help us image. To begin, I want to discuss the celestial sphere. The celestial sphere can be thought of as an imaginary sphere that surrounds the Earth that is used to map the night sky. Every single deep space object can be projected onto this sphere, meaning every object can be thought of as a position that lies on the sphere. Even if two stars seem close together from Earth, they could be separated by thousands of light years. But to us amateur astrophotographers, it doesn't matter. Now let's look at the Earth's poles. There are two commonly referenced pole systems: the magnetic poles and geographic poles. The magnetic poles are the locations where Earth's magnetic field points straight into the Earth. Put simply, they are where the needle on your compass points to. However, the Earth's core is not solid, so its magnetic field slowly drifts over time. As a result, the direction of these poles also moves. But when astronomers and astrophotographers refer to the poles, they are talking about geographic poles. Geographic poles represent the direction along which Earth spins about its axis. They are called true north and true south. This distinction is necessary because when we learn how to set up our gear, and when we use the poles as a reference point in our coordinate systems, we will be using the geographic poles to do this, not the magnetic poles. If I extend these poles through the celestial sphere, you will notice that they intersect the sphere at 2 points. These points are called the North Celestial and South Celestial poles. If you look up at the night sky, you may notice that the stars rotate about a point in the sky. The point that the stars rotate about are the celestial poles. Stars will appear to rotate clockwise about the South Celestial pole and anti-clockwise about the North Celestial pole. In this example, since the stars are rotating anti-clockwise around the celestial pole, we know that we are looking at the North Celestial pole. Now that we have established the poles, let's discuss other important features of the night sky. Imagine yourself in an open field. This surface will represent our horizon. Each horizon is unique. Two people standing close will have similar horizons, but two distant people will have completely different horizons. Now let's say that north is facing towards our right. Then the celestial poles will also lie along this direction. And since each horizon is unique, the celestial poles will be at different heights in the sky, but will always be found in the direction of the North and South Pole. Now let's look directly above our head. This point represents the highest an object can rise above your horizon. It is called your zenith. Now if we draw a great circle passing through both celestial poles and your zenith, we get the celestial meridian. When an object passes the celestial meridian, it is called a transit. I just want to make a quick note. Some objects never set below your horizon. These objects are known as circumpolar objects. As you can see, every object within this circle is a circumpolar object. For these objects, they go through both upper and lower culmination. Upper culmination is when an object passes through the highest point above the horizon. Lower culmination is when an object passes through the lowest point from the horizon. Since non-circumpolar objects do set, only upper culmination can be observed. Even though lower culmination occurs, we cannot see it. You might be asking yourself, why does this even matter? Why do we care when an object is at its highest point? Well, the air in our atmosphere causes distortion and can be bad for imaging. This is why telescopes in space are such an advantage, since the atmosphere isn't bending and warping light, so they can get clean images. Unfortunately, we are on Earth and must deal with this atmosphere. The further light has to travel through air, the more distorted the object you're viewing becomes. The light that travels directly from your zenith towards you has to move through less air than the light that travels from your horizon. So the higher the object is above the horizon, the less distorted it is by atmospheric conditions. For wide field astrophotography, which we will be focusing on mainly throughout this guide, altitude won't matter too much. But as we move to longer focal lengths, this will become more important. Now let's look at different coordinate systems. There are two systems that we will be using on our journey: horizontal and equatorial coordinates. We will mainly be relying on equatorial coordinates to find objects, while horizontal coordinates only find its use in a few instances, but you will see why both are critical to your imaging. Horizontal coordinates are centered around the viewer. If two people were to be staring at the night sky in different locations, suppose one is sitting near the North Pole and one is sitting near the equator, if they both look at a star, such as the North Star, it will appear to be in different positions in the sky. Since horizontal coordinates are centered on the viewer, they will record a different set of coordinates for the North Star. So how do we define horizontal coordinates? Let's quickly go back to our old example, when North was on the right. Horizontal coordinates are split into two parts: altitude and azimuth. Altitude is a system that ranges from -90 to 90 degrees. Your horizon represents 0 degrees, your zenith represents 90 degrees, and directly below your feet represents -90 degrees. Azimuth ranges from 0 to 360 degrees, with 0 degrees being in the direction of north, and it increases as you go clockwise. So north is 0 degrees, east is 90 degrees, south is 180 degrees, and west is 270 degrees. Since the stars slowly drift throughout the night, that means that the coordinates defining their position will also change as time passes. Let's say I am currently sitting at a latitude of 45 degrees on Earth. This dot will represent where we are currently pointing. If I wanted to point towards the North Celestial Pole using horizontal coordinates, how could I? Well, we know that the North Celestial Pole will have an azimuth of 0 degrees, but what about the altitude? Well, luckily the altitude of the celestial poles is exactly the latitude of where you are standing. So since I am at 45 degrees latitude, the altitude will also be 45 degrees. So I can move my mount to 0 degrees azimuth and 45 degrees altitude. Now my mount is pointing directly at the North Celestial Pole. It might seem like I have chosen this point since it is convenient, but what we have done is one of the most crucial steps in astrophotography. What we have achieved is polar alignment. Polar alignment is significant because it allows us to do two things: use equatorial coordinates and follow the rotation of the Earth. I will cover polar alignment in more detail in a future video where we set up our gear for the first time. The Earth rotates. It actually rotates on a slant, which is about 23.5 degrees. And as you know, the Earth orbits the Sun once a year. Now let's say I draw a line from the Sun to the Earth. I will place a dot where this line intersects the celestial sphere. Now as the Earth slowly rotates about the Sun, if we keep placing points where the line between the Sun and the Earth intersects the celestial sphere, I slowly develop a ring. This ring is called the ecliptic. Now halfway between the Earth's poles lie the equator. If I extend this out to touch the celestial sphere, you get the celestial equator. The point at which both the ecliptic and the celestial equator intersect is called the vernal equinox. To be more specific, the vernal equinox is a point at which the sun crosses the celestial equator, traveling south to north. Unlike horizontal coordinates, which are centered about the viewer, equatorial coordinates are fixed. This is because the coordinates of an interstellar object is based on their projected position on the celestial sphere. So even though celestial objects appear to move in the night sky, they only move because the Earth rotates within the celestial sphere. This is advantageous because, for instance, if I tell 10 astronomers to look at a certain set of coordinates, they can find exactly what I gave them, unlike horizontal, where they would need to find the coordinates of the objects relative to them. The equatorial coordinates are split into two parts, declination and right ascension. Declination is simple. It functions the same as latitude, where the celestial equator is 0 degrees and the celestial poles are 90 degrees for north and negative 90 degrees for south. Right ascension is a little bit more complicated. Right ascension is measured in hours, minutes, and seconds. It ranges from 0 to 24 hours, where 0 hours is the vernal equinox, previously discussed, and it increases as you travel east from the vernal equinox. Equatorial coordinates is the most widely accepted system that amateur astronomers and astrophotographers use for navigating the night sky. But I did mention earlier that we need to use horizontal coordinates to use equatorial coordinates. Why is that? This is a star tracker. It consists of two main components, a base that is designed to move according to horizontal coordinates, and the equatorial mount. As you can see, I can move the equatorial mount in two axes, the right ascension and declination axes. But I can orient this in any direction. So how do I know where to point the mount? Well, we point the mount towards the celestial poles. We polar align. Right ascension rotates your telescope around the sky in the same path as Earth's rotation. That is, when we turn the mount, it should spin about the celestial poles, like the stars. This is why we need to align the right ascension with the poles. Horizontal coordinates help us physically align our mount, after which equatorial coordinates allow us to explore the night sky. Now that we have established some of the main systems we will be using in this series, what can we do to find the coordinates of an object we want to image? This is what catalogs are for. Catalogs such as the New General Catalogue, Messier Catalogue, and the Index Catalogue contain data about the objects we want to find. For instance, if I want to image the Orion Nebula, and I want to know where it is in the sky, I can search up something along the lines of Orion Nebula designation or catalogue number, and it will provide a list of catalogs that it has been recorded in. You can also use apps such as Stellarium and StarChart, which give you visualizations on where these objects are. In this video, we have discussed significant positions in our sky, such as the celestial poles, zenith, and the vernal equinox. We have also discussed the different coordinate systems we will be using, but I haven't provided any real examples of star hopping or using databases to automatically find where your gear is pointed. But in this video, I really just wanted to show you the theory behind what will be an important aspect in your journey. Once we cover a few more things such as discussing the different objects you can image and the gear we need, I will take you out and show you practical examples of setting up, star hopping, and using these systems we learned today. Thank you for watching. I'll speak to you soon.